Welcome back. We didn't have a lecture last week because I did the review as part of the week before. We're now going to have our one and only lecture on relativity. And what we're going to focus on is Lorentz transformations and four vectors. So getting into it, something that's important in relativity is what we call four-vector invariance. And two such four vectors are the space-time invariant that we're going to look at today, and the energy momentum four vector, which is extremely useful in a lot of your particle physics calculations. So what the four vectors are something, they define something that doesn't change regardless of the reference frame you're in. So the example for the space-time is I have an object and it is going to flash out let's just make it simple. We're going to talk about light. It's going to flash a light. And in some time t, that light travels a distance ct. And so it makes a sphere with a radius of the sphere of light is speed of light multiplied by time. But we can also use the Pythagorean theorem to find what the radius is in terms of x, y, and z. So we also have that using the Pythagorean theorem. Now this is a three-dimensional Pythagorean theorem. Radius is equal to the square root of x squared plus y squared plus z squared. And so if I combine these two, I should have, and I'm just going to square them. So I'm going to do radius squared equals radius squared. And I get c squared t squared equals x squared plus y squared plus z squared. Or what we usually do is we move the x, y, and z across, and we have 0 equals c squared t squared minus x squared minus y squared minus z squared. And so this defines an invariant. It's always going to be that c squared t squared minus x squared minus y squared minus z squared equals 0 in any reference frame. So that's the idea of our invariant. And so this is just going through the steps of what I just did. You can review these at your leisure if you like later. But it's saying we have two reference frames and we are going to flash the light. We're going to make them so they overlap. So if time equals 0, then their origins are at the same location. They both agree it's time 0. And we flash the light then. And then we have V is in the x direction. We just arbitrarily define the x direction as the direction of the relative velocity to keep life simple, to make this a one spatial dimension problem. So now we've already talked about the spatial invariant. The radius minus the radius is 0. And so these are just going through what I already did. And so here's the invariant that we calculated a few slides back. And so this describes a four space. For space, we have what we often call x0, x1, x2, and x3. So I show them here as a column vector. It's a vector represented by a column. And if I want to find the length of the radius, well, we would use the Pythagorean theorem, which normally the Pythagorean theorem is, r squared equals x squared plus y squared in 2 dimensions, or r squared equals x squared plus y squared plus z squared in 3 dimensions. This one here, the Pythagorean theorem, is a little different. In all cases, r squared is equal to r vector dotted with r vector. But we have to do our dot products just a little bit differently when we're doing these four vectors. And so what we do for the dot product is, notice I have the column vector, they were all positive. If I change it to a row vector, then the signs of the x, y, and z columns components flip, but the CT one, the x0, doesn't flip. And so if I take the dot product r squared is equal to r dot r, it's this multiplication. Remember, from multiplication of vectors or multiplication of matrices, you take the first item times the first item, plus the second item times the second item, plus the third item times the third item, plus the fourth item times the fourth item. You're only multiplying the parallel parts when you're doing a dot product. And so when you do that, and my circles, of course, make it look bad, you get the thing that we just had. So that's a little bit tricky about how we do the dot products with these four vectors. Now, we already learned about Lorentz transforms. That is the time dilation, length contraction. So we have delta t, or I'm going to drop the delta here. T is equal to gamma t prime was our time dilation equation. T prime and t, I put the prime in the wrong place. And x prime is equal to gamma, x over gamma. Wow, it's working out today. X over gamma was our length contraction equation. So we're going to use these Lorentz transformations with just plain general physics things to develop something cool. Actually, the Lorentz transformations. These are time dilation, length contraction. Lorentz transformations are the end result. So for two inertial reference frame, the position time in one reference frame should be linearly dependent on the position time in the other. So here's a way of writing linear dependence. T prime is equal to some constant multiplied by time plus some constant multiplied by position. And likewise for x prime. Or using linear algebra, we can write that same set of two equations with t prime is equal to at plus bx. And similarly, x prime is equal to ct plus dx. So this is just a representation of the same equations, but writing it in matrix form. Matrix form is easier for this kind of math. Now we're going to get out of matrix form, but we'll come back to it at the end. So let's suppose that at time equals 0, these two origins overlapped and there was a flash of light. And sometime t later, okay, that's supposed to be a perfect circle around here, as measured in reference frame S. So S is our unprimed frame, S prime is our primed reference frame. So at some time later, this origin has moved a distance of vt, and the light has extended in the prime reference frame by a distance of ct prime. So I have, okay, that was to the wrong place. I got to pay attention. I should have gone here and here. And just looking at the horizontal distances, we have the distance measured in, and I know this is shown upward, but it should be in the x direction. The distance that is measured in the unprimed frame is going to be x in the unprimed frame is equal to this distance that the reference frame moved of vt plus the contracted distance. So x prime is this distance here, measured in the S prime reference frame. We have to contract it to get it into the S reference frame. So that's the distance that this event is in the S frame using the speed at which the reference frames differ and the distance it is in the S prime frame. And so if I take this and I just want to solve it for x prime, I'm going to have to multiply everything by gamma. Well, first subtract vt, so I'll have x minus vt is equal to x prime over gamma. And then just multiply everything by gamma. So those cancel. And I have x prime is equal to gamma times x minus vt. So here I have my relationship to transform from x and t to x prime. I hope I, yeah. So we can do the problem in reverse. We can go back and look at the same thing and say, okay, get rid of all of this stuff. And how is the distance? Sometimes it won't allow me to erase lines. I haven't figured that out. What is the distance if I go from this reference frame to S prime and look at the S? So for the S prime reference frame, they say, okay, this distance here, instead of being VT, is VT prime because they measure time at a different rate. And they have the distance that they measure is X prime. And they have to say, well, what is the X distance? Well, if you go through it, they have X prime is equal to minus VT prime, minus because it's in the opposite direction. And then X was the length measured in the other frame, and they contracted it for their frame. And so this is essentially the same work, just from the opposite reference frame. So now we have two equations. We have that combined with what we had before, which was X is equal to gamma times X plus VT. That should be the same thing we had from 2 slides ago. Or gamma times X minus VT, excuse me. So this is what we had 2 slides ago. This is from just above. So, of course, X prime should equal X prime, so we just set these equal to each other. So this here, there, and this here, there. And now we only have 1 prime in this. We have T prime. We already had an equation for X prime, so now I'm looking for T prime in terms of X and T. So I need to solve this for T prime, so I have to move this over here and move that over there. So I have VT prime is equal to X over gamma minus gamma times X minus VT. Well, I have X in 2 places, X here and X here. So I want to combine those. So that's equal to X times 1 over gamma minus gamma VT. Okay, ran out of space. You know what you do when you run out of space? You move things over to give you more space. So there's an equation for VT prime. Well, let's divide everything by V, so it's T prime. And then I have T prime is equal to X over V times 1 over gamma minus gamma T. And do I have all my signs right? No, plus. Minus and minus makes it a plus. And you look at this and you say, well, that doesn't look like what's above, oh, Richard. Well, I wanted to factor out a gamma. So if I factor out a gamma, I'll put a gamma out here, which means that I had to put that all over gamma. So 1 over gamma squared minus 1. What is 1 over gamma squared minus 1? 1 over gamma squared is equal to square root squared of 1 minus v squared over c squared. In other words, it's 1 minus v squared over c squared. So 1 over gamma squared minus 1, or I put that the wrong way. Is minus v squared over c squared. So that means that this is equal to factor out the gamma. I have t minus, and then it was, I totally am out of space again. Good thing we know this trick about sliding everything over, right? No, equals gamma times t minus, and then it was v squared over c squared over v, or x times v squared over c squared over v. So that's going to be just 1v on top. And that's what we have above. So it is the same thing. So now I have equations that say t prime is gamma times t minus x v over c squared, and x prime equals gamma x minus vt. So I can fill in that little matrix I had before. That is, t prime is equal to gamma times, those gammas everywhere, so that's what's up front. And then it's t, 1 times t, minus x times v over c squared. And x prime is equal to gamma times minus v t, and then plus x. So it's the same two set of equations. We found what a and b and c and d are. Now, we usually simplify this a little bit, and we multiply t by c. So if I do tc, I'm going to have that. And so if I put that in here, ct prime is equal to gamma times c. That is going to cancel this, right, c over. So v over c. And then x prime, oh, and I need to see here. And so this is going to be, oh, that remains one. Yes, the c needs to be there. So ct prime equals gamma times ct minus v over c x. And x prime is equal to v over c times ct, gamma times minus v over c ct, and then plus x. And so we could write this as gamma times 1 minus beta 1 ct x. And that's usually how we write a Lorentz transform. Right, we use the ct rather than just t. So if we do it in all 4 dimensions, 3 spatial dimensions, and the time dimension, what we've just found is these 2 relations. And notice this is changed to x0 is equal to ct. So this is changed to what we had right here. That is x0, x1 prime equals gamma 1 minus beta 1 x0, x1, which gives us x0 prime is equal to gamma x0 minus beta x1, and x1 prime equals gamma times minus beta x0 plus x1. And so those are the relations, just the order of x1 and x0 I flipped in the second one that we show here. What about the y and z directions? The y and z directions are unchanged. Remember, length contraction was only parallel to the velocity. So the y and z's are changed. Now we can shift to x0 and x1 in terms of x0 prime and x1 prime by simply changing the signs of beta, because beta is the velocity divided by c. In the prime frame, the velocity of the unprimed frame is the opposite direction from what it is in the unprimed frame. That is, if I have, here's my S frame, and here's my S prime frame that's moving at speed v with respect to S, then if I reverse my view, S prime sees S moving away at speed of S Okay, speed of s prime. I got my things wrong there. The speed of s prime with respect to s. Speed of s with respect to s prime is equal to minus v. What is this? It's equal to v. And so that change in sign is why the betas are shifted. So how is this useful? Well, we're going to use this to calculate addition of velocities. Now, you saw in class what the equation was for parallel velocity addition. We're going to look at both parallel and perpendicular addition of velocities. So just like in class, we're using u is equal to the speed of the object, and v is equal to the speed of s prime with respect to s. And so we just have the definitions of speed. So the speed in the x direction is dx dt, speed in the y direction dy dt, speed in the z direction is dc dt. Or if we're going to do, x prime, it's, speed in the x prime direction, that is, as measured in the prime frame, is the derivative of distance in the prime frame divided by derivative of time in the prime frame. Well, that's real simple, right? And then we have our Lorentz transforms, which relates the primed and unprimed frames. So let's get to work on this. And this is going to require me to add just a few pages. Insert, let's add 3, just to make sure we have enough space. So let's find ux prime. So that's equal to dx prime dt prime. We know that x prime is equal to gamma times x minus vt. And gamma is invariant, or gamma does not change when I shift from one reference frame to the other because it depends on v squared, and the differences in v's were minus 1. So what I'm going to do is I'm going to take this and I'm going to say dx prime is equal to gamma times dx minus v dt. So there's my dx prime. And then I'm just going to say, well, if I do the same thing with t, dt prime is equal to gamma times dt minus dx v over c squared. And so if I want to find dx prime dt prime, I just have to take the division between those. And so I have that's equal to gamma times dx minus v dt over gamma times dt minus dx v over c squared. So far, so good. But, we have d's in here. How are we going to do this? Well, here's a little trick. Well, let's start with something that's not a little trick. These gammas cancel very clearly. So here's the little trick. I'm just going to take each one of these and put over dt. So I multiply top and bottom by dt in essence. But then that simplifies because dx dt is, of course, ux. So this is equal to ux minus v, and then dt by definition is 1, over, and on the bottom I have dt, that's 1, minus dx dt, again, ux v over c squared. And there you have it. There's the equation for the addition of velocities, as you have the velocity of your reference frame and the velocity of the object. And so the way we would have written this in normal class, I would have said the speed of my object with respect to s prime is equal to the speed of the object with respect to s minus the speed of s prime with respect to s over 1 minus the speed of the object with respect to s, speed of s prime with respect to s over c squared. Now you might look at this and say, wait, that's not the same as what you wrote in class. But it is, because remember, vs prime s is equal to minus vss prime. And so this would be equal to and that is the way we showed it in class. So that's how we add parallel velocities. That is, if v is in the x direction, that was our definition, and ux is in the x direction. But what if it's not parallel? What if it's perpendicular? So let's do uy prime. So if I want to do uy prime, I start with our equation. Uy prime is equal to dy prime dt prime. And just like before, I used my substitutions, but dx prime was complicated. Dy, that's a simple relationship. Dy prime is equal to dy. So this is going to be dy. Right, that was simple. And of course, the dt stays exactly the same as it did before. So just looking at what we had before, dt prime is gamma times dt minus dx. V over c squared. And using the same trick as before, I divide everything by dt. And I end up with dy dt is uy. Notice I couldn't cancel my gamma this time. Dt dt is 1 minus ux. Now that's a little different, just a little different. Now if I want to put it with subscripts like we did before, that would be u of object with respect to s prime is equal to u of object with respect to x divided by gamma times 1 minus u of object with respect to x, the speed of s prime with respect to s over c squared. Or to put it in the way that would be more like what we did in class, whoops, ss prime was what was the whole point of this. And so this here has subscripts for everything, so it makes it, well, so is the one above. It makes it easier to apply, but this form here has the same denominator as that form there did, except for the gamma, because the gamma couldn't cancel. So even though we don't have length contraction in the y direction, when we add velocities, the addition is a little bit more confusing. And you might wonder, why is it a little bit more confusing if it was, kind of straightforward in terms of there's no difference when we add distances? It's because time is passing at a different rate. Even though the distances are the same, time is passing at a different rate, which means that the speed, the distance over time, is different. So here are the outcome equations. So this is the way that we found them directly without doing any conversion to make it match what we did in class. And just like before, if I wanted to switch where my prime is, I just change the sign of the speed. Yeah, actually, these here are the ones we just found, and this is converting to the reverse. So you just change the sign of the speed in each equation to reverse x versus x prime or y versus y prime. So that's how we do relativistic addition of velocities. And I think it's really cool because using calculus, we can show how these weird old equations are pretty straightforward coming together. All right, have yourself a good day. Goodbye.